begin. All right, so how many of you have taken some physics classes? Couple? All right. When it comes to 12.4 and applications of double integrals, there are several topics in this section that I could cover, but we can't cover them all. And it's not a full treatment of each of these applications. So I picked one that I'm going to do just to show you something. You may or may not have seen this before. But what I'm trying to say is that there's about 4 or 5 different applications in the section. We're only going to look at one. We just don't have time to go through all the rest. All right? So I thought I made something here today. I'm pretty excited about this. We have these 2 cardboard pieces that I cut out, and they're supposed to be pretty much the same. Do they look pretty much the same to you?
Are they like wisdom teeth or mobile?
No, it's just some random shape that I came up with. So what I'm going to do is I'm going to start out by talking about the center of mass of this object. Now, center of mass, we need to first describe what this object is. So we call this a lamina. We're going to look at it as a 2-dimensional object, not 3-dimensional, even though it is 3-dimensional because it has thickness, right? Let's just imagine this is a sheet, and that at every point you have some mass at every point. All right? So the center of mass of this object will be the point at which I could balance this object on one finger. Let's see. See if I can find it. I found it earlier. Boy. That's assuming that the density is uniform, which is what I'm about to talk about. So I found, I think, the center of mass. Now there's another way to do it that's a little easier than balancing it on your finger. There's a more precise way of doing it. Anyone know how I can do this? You can do this for any sheet. You can attach it maybe like with a tack or something and hang it, and then drop a string attached to something that is just hanging with gravity, and then draw a straight line down through that string like that. And then just grab it somewhere else and do it again. And then, just to be more precise, grab it somewhere else, like, I don't know, here. Here. Okay, and then draw a straight line down. And this should be the center of mass. All right, so if I balance right here, I should be close. It's not close. But my line was not very precise either, the one I drew vertically. But that's the way you can do it. So if that's my center of mass, then if I actually throw this object up in the air like this, you see the point? Look at the point. Yeah, the point, just the point goes straight up and straight down. So it rotates along, it rotates along this center, it rotates along its center of mass, all right? Okay, now I have another one right here, same object, right? And I'm going to find its center of mass. They should be pretty close to the same. Let's see here. That's kind of weird, huh? I'll try and rotate this one. Did I do okay on that one? Yeah, it's okay. Different centers of mass. What's going on here? Well, here, let me do. What's that?
Can you have 2 different centers of mass?
Yeah, I mean, if they're the same shape, shouldn't they have the same center of mass? Yeah? Well, I attached a bunch of paper clips to the back of this one, okay? So what I did is I changed its mass, its distribution of mass. In other words, I changed its density at different places. So this cardboard is what we call homogeneous. That means that at every point, the density is the same. How much mass is at every point is the same. Homogeneous. This is non-homogeneous because I've actually changed how much mass is at every point. And so these should not have the same centers of mass, right? In Calculus 2, you can find the center of mass of a homogeneous object. Okay, in Cal 2. It's an application of double integrals. It's an application of integrals that I usually don't do in my Cal 2 class. Because when we get to Cal 3, we have a way of finding the center of mass of either a homogeneous or a non-homogeneous. This is non-homogeneous. So we're going to find the center of mass of something like this. Now, in order to do this, you actually have to know the density of your object at every point in time. At every point. On every point, you need to know what the density of the function is. So if there's more mass, let me turn it around so you can see it. So if there's more mass up here, right, you're going to have a higher density up here and a lower density down here, right? Understand that? You need to know the function that gives you that density in order for us to find the center of mass. Now, on a topic that's slightly off topic, but at the same time related to this is a story I heard. I don't know if it's true, but it's a good story. There was a challenge problem given to some students at MIT many years ago. I heard this when I was a student. So the challenge, I don't even know what class it was for or anything else, just some students at MIT were given the challenge of trying to approximate the area, the square footage of the MIT campus. Okay? That was their goal. So the professor broke them up into groups, said, y'all go figure it out, we'll come back, and we'll see who has the best answer. Okay, the best approximation. So different groups did different things. The winning group, okay, what they did was they counted on the fact that if you have an object that has a homogeneous density distribution like this, they counted on that fact, and here's what they did. They went and they pulled up a very precise map. Okay, and on that map it had the MIT campus, which I'm just making up. Here's the MIT campus, right? There's MIT. And they took this map and they cut out MIT. They cut out MIT from the map, all right? And then they weighed that piece of paper. Got it? And then what they did is they took another sheet of paper, same type of paper, and they just cut out a rectangle and they measured very precisely the dimensions of the rectangle and they weighed that. And what they did is they set up a proportion. So think of it this way. If I know, let's say this was 8 by 12, an 8 by 12 sheet of paper, then I know its area, don't I? Yes? And they used, they used the legend over here that they knew, you know how they have the little legends of, how far something is, like 0 to maybe like 500 feet or something like that. They were able to say, okay, if this is an 8 by 12 paper, they take this over here and they measured out like how many hundreds of feet that would be, and they were able to find the area, like the physical area on the map of what this would be, and then got that area over its weight, and this was for the rectangle that they cut out, and that should be proportional to the area of MIT over its weight. Understand? They know this, they could weigh that, they could weigh the paper, they knew the area of the paper, and they solved for area of MIT. That was the best answer. While other groups were out there like, go down there, tape measures, and trying to figure it out. So, pretty clever, huh? But that counts on the homogeneous nature of paper. We know that paper is not homogeneous, not completely. Enough for this application, sure. But in real life, this cardboard is not homogeneous, right? There's differences as you move around, but we can consider it homogeneous. Y'all understand? Okay. All right, so our first application for double integrals is our goal here is going to be to find the center of mass And then the second goal, after we find the center of mass, is to find what's called the moment of inertia of a lamina. So, have y'all heard that before, what moment of inertia is? Do y'all know what inertia is? What's inertia? Can someone describe to me? Anyone? Inertia? Yeah, that's basically it. Inertia is the resistance or tendency of an object to not want to move. If it's at rest, its inertia is a measurement of its resistance to motion, acceleration. Or if it's in motion already, it's its resistance to stopping. So I remember this story. I mean, this isn't a story. This happened. I was sitting. My grandma used to live in California. We saw her very few times in our lives. And my brother and I went. We were both in college, and we went to visit her. Her health was kind of declining, and we went to visit her. And she was driving, and she had modified her seat belt so that she could click it so that the dinger wouldn't go off, but there was no belt. So she basically just like cut the belt off. And she's driving, and we see that, and we're like, what's going on? She's like, I don't believe in seat belts. And my brother's like, but do you believe in inertia? You know, because I mean, that's what, when you get into an accident, right, that's what hurts you, right? Your body is moving. It doesn't want to stop moving. You hit a brick wall, it keeps going, right? That's what kills you, is the inertia. So, all right, inertia, grandma. So we want to find what's called the moment of inertia of this lamina about some axis. So like if I take this lamina and imagine that I have like the y-axis here. And let's say that I want to take this and I want to rotate it around the y-axis. So imagine it's somehow connected to the y-axis on some arm, and I'm gonna push it, almost like the door, okay? Like that door is sitting there. It's on an axis and I want to rotate it. So the moment of inertia is going to be a calculation that gives us a numeric value for this object's resistance to that motion. So we'll have a moment of inertia calculation for this. What would happen if I move this object further away from the y-axis? Will its moment of inertia increase or decrease? It actually increases. So it would be harder to move this object around that axis if it's further away. All right? And so there's a formula for it, and we'll do it. But we'll be able to actually calculate a non-homogeneous lamina's resistance to motion about the y-axis. We can also do it about the x-axis, and we can also do it about the origin, which is like almost like a diagonal cross. All right, that's where we're headed.
Is the inertia, I don't remember, it's rotational, right? When we're speaking.
Right now, I'm talking about, yes, inertia with respect to an axis. Because you can have rotational inertia, like if you have like if I cut out a disc like this, and let's say I cut out another disc, but I cut out the center like that. And then I start rolling them down an inclined plane. That's rotational inertia, all right? I mean, for inertia, we don't have to have rotational, okay? Because this object, if I just try and move this, right, like this, that's not really rotating about anything. I don't know if I'm answering your question. Okay. All right. Where's my thing? All right, so remember, first of all, that density is mass divided by volume. But if it's a two-dimensional lamina, we are going to say that density is mass divided by area, which is a little weird because area is only two-dimensional. But that's how we're going to define density for this lamina. Mass divided by area. So suppose that the density is variable, meaning the density at every point in the lamina may be different. That's this guy right here. The density at every point is different. Then the total mass of the lamina, is the sum of the mass at infinitely many infinitesimal rectangles. So imagine cutting up this lamina right here into an infinite number of rectangles. And at each rectangle, calculating the mass. And then adding them up, right? This is a double integral. That's exactly what we've been doing, right? We took some region, we cut it up. Now this was more like a type 1, type 2 region because we're not using, these are not polar rectangles, right? These are your traditional Cartesian. So if we cut up infinitely and then calculate, normally we thought of a function above this, didn't we? Like above that, we imagine a function. Well, that function now is just the measurement of the mass there. Okay? And so it's a numerical value. You could visualize it too, but for us, the numerical meaning of what's happening above this rectangle is gonna be the measurement of the mass for that little piece. So we just go through and all we do is we take, sorry about the colors and the bad handwriting, but if you take this little rectangle, the area of this rectangle is dx dy. We've already seen that before. And we pick some random point inside the rectangle. Remember I said we have to know the density at that point. So let's say we know the density. The density is given to us by rho of xy. So I put it right here. Rho of xy is the density function. This has to be given to us. Then if we take the density equation, density is mass over area, and multiply both sides by area, we get mass is equal to density times area. Density is the rho function, and the area is dx dy. So the mass at that little infinitesimal rectangle is going to be the density function times dx dy. Then to add them up, we do the double integrals, or the double integral. So we're going to sum up all these little masses. So that's it. The mass is the double integral over your region D of the density function with respect to area. That's what this says right here. That's pretty cool. Now, we can also do another application. Now, I'm not going to get too heavy into this, but that density function, you could change that to any other function. It could be the temperature at each point on the lamina, right? But then what would the double integral mean? If I took the temperature at each point, instead of the density at each point, the temperature at each point, and then added those all up, what would that mean?
The average temperature.
Would it be the average temperature? It would be like the sum of all the temperatures, wouldn't it? Now you could get an average, right? If you somehow were able to then divide it by the area or something. So you could get the average temperature, but it wouldn't have a lot of physical meaning to add up all the temperatures, would it? Adding up all the masses, that has some physical meaning, right? It would be the total mass of this. Well, we can do something that does have meaning, electrical charge. If you take the electrical charge measurement at each point, so imagine this lamina has a charge to it. At each point, there's a different charge, a variable charge. Then we would have sigma xy is a charge density function, so instead of rho of xy, and then you could have the total charge would be the double integral. Same exact story, just different meanings for the numbers. We're not going to get into that. All right, we're going to do this example. A lamina is formed by the region bounded by y equals 1 minus x, y equals 1, x equals 1. The density at the point xy is given by the density function rho of xy equals x times y. It's okay. That reminded me I forgot to turn mine off, but no one calls me. Unless they want something. Okay. Come on. All right, so find the total mass of the lamina. Remember, our goal is to find the center of mass, right? All we're doing right now is finding the mass. We actually need the mass to find the center of mass. So let's do this. The mass is equal to the double integral over the region D of the density function with respect to area. That's our formula for mass. Now let's draw our region. Our region is the region bounded by, So this is the lamina. When they say the region, this is the actual lamina I'm about to draw. Y equals 1 minus x is a line like this. Right? X equals 1. X equals 1. Wouldn't that also be right here? Right there? So x equals 1. This is going to get in my way. X equals 1. Y equals 1 minus x is that one. And then what? Y, oh, I missed the y equals 1. Y equals 1. Nah, I'll just do it in black. So y equals 1 is here. So there's my lamina, right? Pretty simple lamina. The density, okay, the density at every point on this lamina is different. And the density is actually given to us by this function. So I have a question. What is the density at the point 1, 1? I'm saying, what's the density right here? It's 1, right? Because you're just doing x coordinate 1, y coordinate 1, plug that in, 1, 1, you get 1. What about the density right here at the point 1, 1/2? It'd be 1/2, right? The density is 1/2. Understand? You would also have the same density here, right? Wouldn't that be, if that's 1/2, 1? So these 2 points would have the same density, wouldn't they? What about along the diagonal line? What would the density be along that line? Would it always be the same or no? It would be the x value. So like, what's the value here? What's this value right here? This is 1/2, right? So do you all agree this point 1/2, 1/2 is right there? What's the density there? 1/4, right? It would be the x value squared. Anything along this dotted line would be the x value squared, wouldn't it? But out here it's different. So what I'm trying to get you to see, again, is that it's these paper clips. As you move along, your density is different, all right? But this is the function that's dictating how that relationship is made. This would be a very weird density function. All right. That's pretty much all we need. We need to do a double integral over this region. So we look at the region and we have to determine, do we want to look at it as a rectangle or a type 1 or a type 2 or a polar? Because those are the only things we've got at this point, right? So what do you think? Type 1? I think that's a good type 1. If this is a type 1, then my x should be between two constants and my y should be between two functions of x. So my x values are between 0 and 1, and my y values are between, let's see, the red function, right, is what's dictating the bottom. So what is that? 1 minus x. And then the top function is actually constant all the time, isn't it? It's the constant 1 function. So this would be 1. And so this double integral will turn into integral from 0 to 1, integral from 1 minus x to 1 of the density function xy, right? Rho of xy is xy. And then dA, I'm going to write that as what? dy dx. I believe this integral is doable. Do you agree that this is pretty straightforward? You integrate that with respect to y first, plug in 1 and 1 minus x for y, and then do that, and then integrate that with respect to x, and then plug in 1 and 0, subtract, and you're done. I don't think I'll do that problem. Is that all right if I don't do it? Okay. So this right here would be the mass of this object. Understand? Okay. Now, what I will do, just so we have the answer, because I'm going to want the answer here in a second. Let's actually compute it so we have it. I'm going to cheat. I'm going to use the computer to do it. So make this a little bigger so you can see what I'm doing here. Go from 0 to 1, and then 1 minus x to 1 of x times y dy dx. 5/24. Okay, that would be the mass of that object. Keep that on the back burner. We're going to need that. All right, next one. Charge is distributed over the region bounded by y equals 1 minus x, y equals 1, x equals 1, such that the charge density at the point xy is given by the function sigma xy equals x times y. Find the total charge. What is that? Same answer, right? That's the exact same setup. All I'm doing there is just using the different language. The first one was mass. We calculated mass. Here we're calculating total charge, but the setup's exactly the same, all right? So we're not going to do that one. All right, now we're going to talk about, we're trying to get to center of mass. That's what we're trying to get to. We need to talk about what's called the moment. And unfortunately, this is not a physics class, so we're not going to get it too technical into definitions. But the moment about an axis. Suppose we have the lamina, okay, in the xy plane. Then the moment of the lamina about the x-axis, not the moment of inertia, the moment is about the y-axis is given by this symbol, capital M subscript x, the moment about the x-axis. It's the double integral over d of y times the density function, rho of xy, with respect to area. So what has been modified? That formula looks very familiar, doesn't it? Yes? The y is in there. So look, here's what's happening. Before, what we were doing was we were cutting up this lamina into tiny little rectangles, right? And we were finding the mass at that infinitesimal rectangle, right? We were finding that mass, that tiny little thing. Now, instead of finding the mass at all these rectangles and adding them up, I'm taking the mass, right? The mass is this part. All of that was the mass. I'm multiplying it by what? Y, which is a distance. It's the y coordinate coming out here to your rectangle, the y coordinate. So it's actually the mass, right, times the distance from the axis. This was, oh, sorry. Oh, I labeled this wrong, please. They should have caught me there. It's about the x-axis. So it's from the distance from the rectangle to the x-axis is y. This would have been what? X, okay. So that distance is y, isn't it? Okay, so we're taking the mass there and we're multiplying it times that distance. Understand? All right. That's called the moment. If you add up, for each little rectangle you'll have a little mass and you'll have a different y, right? Every one of these. If you add all those up, you get what's called the moment of the lamina about the x-axis. Now, we can also do the same thing. We can calculate what's called the moment of the lamina about the y-axis, and that's what I drew just a second ago incorrectly. Take a little rectangle, and this time do the distance from here to here, x. X times this part, which is mass, gives you the moment about the y-axis. All right. That's right. So if we look at the example 1, right, and we were asked to find the moment about the x-axis, the only difference would be that we would put a y inside next to the density function. It would be xy squared. Yep. We're about to do it, but that's what would happen. Okay, so now we get to finally the formula for the center of mass. So suppose we have the lamina in the xy plane. The center of mass is denoted, we use the notation x bar, y bar. Okay, that's the notation we use, x bar, y bar. Where x bar, which is the x coordinate of the center of mass, okay, the x coordinate of the center of mass is going to be the moment about the y-axis divided by the mass, the total mass of the whole thing. Now, do you remember what we needed to do to calculate mass? It was a double integral, right? That was the 5 over 24 that we had earlier, right? So we're going to take 1 over 5 over 24 and then calculate the moment about the y-axis, which is x times the density function, and do that double integral. That's how we get x bar. To get y bar, we have to do the moment about the x-axis and divide it by the mass, which is this integral. And remember, the mass, this is what I was saying, the mass is that double integral we started with. Yeah, these are not fun. Well, they're fun, but they're not. They're long, tedious. Okay, so let's start with a problem fresh from scratch, okay? Find the center of mass of the region bounded by x0, y equals x, 2x, and 2x plus y equals 6 if the density function is rho of xy equals x squared. There you go. So let's start by drawing the region. X is 0, right? X is 0 is the y-axis. Y equals x is the diagonal. And 2x plus y equals 6. This right here, if I solve this for y, I get negative 2x plus 6, right? That's what I get. So that means it would hit up here at 6, and then it would have a slope of negative 2, which means it would come down like this, right? This is y equals negative 2x plus 6. Do y'all agree with that? Do y'all see the region? Here's the region, right here, that I'm trying to determine the center of mass of, right? Now, is this region, and before I do this, let me ask you something. What if our region, I want to see what you're thinking here. What if our region for this problem looked like this, and let's say that this was 3 and that was 6, that was 0. Let's say that was our region. Would we still need to find x bar? If we're trying to find the center of mass of this lamina, would we still need to find x bar? Or is it going to be 3? This problem, this object instead. The only way it's going to be 3 is if this is homogeneous. Is the density of this object homogeneous? No, because the rho function, the density changes, doesn't it? Now, I said, I don't cover this in Cal 2 because we can do that in Cal 1. What would I do if this was homogeneous? What would your density function have to look like? It would have to be a constant. Okay? It would have to be a constant. So if this density function is a constant, then you have a homogeneous lamina. But if it's anything other than a constant, then the density of this object changes. So this problem with that density function, x bar is not 3. You still have to go calculate it. All right? That's like what I just did here. You know, I threw off the center of mass with weight at different places. This density function is throwing off the visual center of mass. Does the center of mass of an object have to be on the object? Does not, right? That's what a boomerang is, right? A boomerang's center of mass is not on the object. A basketball, its center of mass is inside the ball. It's not on the surface, right? Okay. What's that? Yeah. 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 That is true. All right. Okay. What do we need to do here? What do we need to do?
Can you do in the y direction?
What direction do you want to do? Type 1, type 2, right? That's what you're saying? Is this a type 1 or type 2 region? It's a type 1. Could we look at it as a type 2?
Yeah.
Yes, but you would have to split it into two. You would have to go like right here, and then you would have like one function on this side, one on this side, and then one here, and split it. I kind of don't want to do that. I want to go top to bottom because this curve up here, this line, is always the top function. This is always the bottom function, right? So I like this as a type 1. But what will we need to figure out? Where they hit each other. I need to figure out where they hit each other because that's going to give me my restrictions on x. So a quick little solution, we have to set this equal to this, right?
Yes.
So if I do that real quick, negative 2x plus 6 equals x, I get x is 2.
Yes.
Okay, x is 2. So I know that that hits at 2. So 0 to 2. So I've got a type 1. I've got x's between 0 and 2. I've got my y's are between what? X and negative 2x plus 6, right? And so my double integral, what am I going to do now? I mean, I'm trying to get x bar, right? Don't I need the mass? I mean, just to start off, let's just get mass because we need mass for both x bar and y bar. So let's do our mass calculation. Mass. For mass, mass is the double integral. In this case, it'll go from 0 to 2, and then it'll go from x to negative 2x plus 6. What am I integrating? X squared dy dx, right? And again, this looks doable, doesn't it? Okay, and again, to save us time, I'm just going to do it here. It goes from 0 to 2, and then x to negative 2x. Wait, where is it? Negative 2x plus 6. And we're doing x times x. The answer is 4. So this comes out to be 4 after some work, okay? So you would have to do that work. These will come up on a take-home exam that I give you. You're going to have to do a center of mass calculation for a triple integral. I don't think I give you a double integral. So we're going to talk about triple integrals next, and we'll be able to find, this is what's really cool, we'll be able to find the center of mass of a three-dimensional object that is non-homogeneous. That's the one it'll be on the take-home. But you got to start with the two-dimensional. All right, we've got our mass. Question? Pardon me, I can't hear you.
It was just the mass that was for?
Yes, just the mass. Okay, now I'm going to go get x bar. All right, so how do we get x bar? To do x bar, I need the moment about something over the mass, right? The moment about it was y. The moment about y over mass. That's how you get x bar. That was the formula I gave you before this. Now, what was the formula for the moment about y? The moment about y is double integral over d. And if you don't remember it, just think about it. Draw the picture. Here's the lamina. You're going about the y-axis, right? Which means the measurement from here to here should be x, right? So this is going to be x. You see this. There we go. There's your x bar. There's your y bar. So I'm doing the moment about x, or sorry, the moment about y is equal to double integral x rho xy dA, which for us is the same integral, right? This same integral, the same exact setup, 0 to 2, x to negative 2x plus 6. But now instead of x squared, it's going to be x times x squared, so x cubed. dy dx. And then we grind that out. Actually, we don't grind it out. My computer grinds it out. (24/5). While we're here, let's do y bar. Y bar is the moment about the x-axis over mass, right? I haven't computed those yet, right? I just got the moment of y. I'm going to put that in there in just a second, but let's get the moment about y. What would that be? All right, the moment about x. I keep on saying it backwards. The moment about x would be double integral over d of y rho xy dA, which is the same exact integral, 0 to 2, x to negative 2x plus 6. But now y times the density function, so x squared y, or yx squared, dy dx. And again, I will go to my computer for this. X squared times y, 48/5. Okay, answer time. X bar is the moment about y, which was 24/5, over the mass. The mass was 4, right? So you could look at that as 4 over 1. Then you're going to flip. Here, moment about x over mass, so 48/5 over 4, which is same as 4 over 1. So what is our center of mass as an ordered pair? 24
over 20.
24 over 20,
48 over 20.
48 over 20, which as decimals was what? 1.2 and 2.4. So if we go out to that spot on that lamina, 1.2, 2.4, we will be at its center of mass. Why do we like to get centers of masses of objects in physics?
So the buildings don't crumble.
What's that?
So the buildings don't crumble.
So the buildings don't crumble? If you have an object that's complicated in shape, right? So like this right here, this is somewhat complicated in terms of its shape, right?
So it's a trajectory, you'll follow it a lot easier.
Yeah, so like what I could do for a lot of applications is I could consider this to be just a single point moving, and then it has a certain mass, and I can talk about this as a point mass moving around as opposed to the whole bottle moving around. So if I can find its center of mass, then I could use that as the point. Understand? And that's one thing. It's just to simplify some of the calculations. Now you can't do it for everything. Sometimes you need to take into account everything about this bottle. So like if I'm going to throw it through the air and I want it to start, flipping like this, then there's a lot of things happening now. This handle being here has an impact on that, right? So you don't always want to turn everything into a point, but a lot of times you can.
So, like, say we have like a binary system, float through space, we can kind of find its center of mass and calculate it as like a point and find out where it's going. As a binary system instead of just like two separate objects flying.
Okay, yeah, so like if you have two objects, you're saying find their center of mass, and they're doing some stuff, just look at it as a single point, if it's appropriate to the problem that you're looking at. I mean, if you are interested in what's going on between them, then of course you don't want to look at it as a point. But you could. You could. All right. Now, the moment of inertia. This is the calculation we can do to figure out the object's resistance to rotation about an axis. So there are three formulas for moment of inertia. The first one is the moment of inertia of the lamina about the x-axis. So you're trying to go rotate this lamina around the x-axis. It's the notation we use is I for inertia about the x-axis. And this is the double integral y squared rho xy. You recognize that, kind of? What was the moment about the x-axis? That's the integral we did just a second ago. It was what, just y rho xy dA? The only difference now is instead of y, we have what? Y squared. And y squared, if you've studied inertia before, inertia is calculated by doing mass times the square of the directed distance. And so the y is your directed distance, and you're squaring it. The squaring has the effect of making anything that was negative positive. So this is your moment of inertia. This is your moment about the x-axis. Square that y, and you get the moment of inertia about the x-axis. And then the moment of inertia about the y-axis is the same thing. You're going to square the x. And then you have the moment of inertia about the origin. And the moment of inertia about the origin is just the sum of those two. You just take those two and add them up. And one way you could look at that is instead of doing x squared in front of the density function or y squared, you add the two and then put them together. So you could distribute this through to each of those and split it apart, and you would see that they're equal to this. So last thing there, the moment of inertia of a particle is its mass times its squared directed distance from an axis. All right. That's it. That's all I've got for this section. Don't have the homework on this for some reason, so I'm going to have to email you the homework. Could we find the moment of inertia for the problem we just did? Right? This problem, we could find the moment of inertia. All we would do is do the same setup, right? And then if we wanted, let's just do one of them. If I want the moment of inertia about the x-axis, it would be the double integral 0 to 2, x to negative 2x plus 6, and then what? Y squared times the density function x squared dy dx. That right there, that numerical value would give us the moment of inertia about the x-axis. Same thing, x squared times x squared dy dx. Which one of those do you think would be bigger? The moment about the x-axis or y-axis? We have to go back and look at this. Our region looked like this, didn't it? Or something like this. They hit at 2. This was up here at 6. What do you think would be bigger? The moment about the x or the y? You think the x? So I guess the larger the number, the harder it is to rotate it. The smaller the number, the easier it is to rotate it. So you think this would be easier to rotate around the y-axis or the x-axis? Well, you have to take something into account here. You have to take into account the density, right? So where's this object the most dense? Ooh. Away, as I move away from the y-axis? So let's just pick a value. Notice the density function only involves x, right? So if I'm right here at 1, what's the density here? 1. And then any point along this line, the density is 1. Agreed? But if I move here, the density at 1/2 is what? 1/4. So it's less dense along this line. And then as I move out to here, what's the density at that point?
2.
2 squared, so 4, right? So very low density, right? Very low density. And then it gets more dense as I move across. So there's more mass over here. You want to stick with your answer of it's easier, where it's easier to rotate? You think it might be the y now? Because you got more mass out here, right? So maybe it's harder. So the only way to really do it is to actually calculate it. I've gone too far. I can't leave this open. Okay, so the only difference here is y squared. Which one? Let's do the first one. Moment about the x, or inertia, moment of inertia about the x. That's that one. That's 128 over 5. I'm going to do it as a decimal. And then about the, no, that was the x-axis. Now about the y-axis, I have to do x to the 4th, basically. 6.4. Wow. So which one was greater? The moment about the x-axis. This way was still greater. Now, the reason why is because this is not drawn to scale. I should have drawn this a little bit better. Remember, where's our y-intercept up here? 6, 1, 2, 3, 4, 5, 6, right? And then we hit it 1, 2, and then it was y equals x, right? So right there, this is actually the region drawn more to scale. So even though it's less dense and then more dense, we've got more mass further away from the x-axis, right? This mass up here, even though it may not be as dense as it is at this corner, this mass is further away from the x-axis, so you're going to get a larger moment of inertia from that. Okay, it is what it is. You can't argue with the math.
You can, you just won't.
Huh?
I said, yeah, you can, but you can't. You won't win.
Yeah, you can argue with it, but you'll be wrong or right. So, all right, that's it. 12-4. We'll call it a week.
All right. Everybody else?
Oh no, I don't want to save that.
Go trick or treat.
I did. It was very nice. Very nice. All right. Triple integrals. I would love to give you the rest of the day off, but we're still behind. Right? Remember, we lost that day early in the semester. We're still trying to play catch up. So, triple integrals. So remember, what we did before, double integrals, you always had, with the double integral, you always had the domain, which was in two-dimensional space, right? But the function lived in three-dimensional space, right? And the double integral was giving us a volume underneath this down to the domain on the ground. So this was your domain on the ground, and then you had the surface, and then the volume below it was the double integral, right? The thing that was great about this situation with double integrals is that you could visualize the domain, you could still see the function in three-dimensional space, and you could see the solid that we were trying to find the volume of, right? And it all made sense physically. We could understand that it's the surface projected down onto the domain volume. Triple integrals, a little harder to, well, You can't visualize it. And that's because for a triple integral, our domain is where? Is in 3D. So these are the points being plugged in to the function. The function is a function of 3 variables, x, y, and z. And so I can't even graph it for you. All right? So what does the triple integral represent? And this is where I had given an example once of, let's say that we have some object here. I'm going to make it simple, like some sort of box. And our function is somehow measuring the temperature at each point on the box. Then the double integral would give us some sort of sum of temperatures, which again wouldn't make any sense. But if you had density at each point, right, then the triple integral would somehow add up all the masses and you would get the mass of that object, which is going to be an application that we do at the very end of this section. But I'm just trying to give you a heads up that we cannot see the function anymore, right? We can't see it. Yeah. Yeah, unfortunately it's not there. Now, I also do want to do one more little review topic here. We had with double integrals, we started out with rectangles, then we went to, what was this? Type 1, and then we did type 2. So this was type 1, this was type 2, this was basically a rectangle. And then the last thing we did was something like polar, right? Okay? We are going to do that all now, but with triple integrals. And you're going to see immediately that we have kind of a lot more situations that we could run into. So that's where we're going to start here. Triple integrals. And here's our first type of region that we have for a triple integral. So this is our domain. A triple integral over a region E, where E is a box. The x's are between constants, the y's are between constants, and the z's are between 2 constants. We're using R and S for our restrictions on z. So there it is. This is some box sitting in 3-dimensional space. That's the domain of your function. Those are the points that are allowed to be plugged in. Now these are not sharp corners because the computer is kind of surrendering a little bit. I should have done a better picture, but you understand those are sharp corners there. Okay, so all the x, y's, and z's that live in here get plugged into some function. A triple integral will add up all those values. What that means physically depends on the problem. All right? Now, I want us to focus on something here. With this solid, if you were to imagine shining a light going up above this object, way up, and shining a flashlight straight down onto the top of that object, you would cast a shadow onto the ground, and that would be D, wouldn't it? And D is what type of region from a double integral? It's a rectangle, isn't it? Do y'all see that? This is important. Your solid here is a rectangular solid. It's a parallelepiped. It's a box. But its shadow cast onto the xy plane creates a rectangle in a double integral. Yes? Okay. This is the most basic triple integral you can have. All the variables are stuck between constants. And as you might expect, the triple integral over that solid E of the function of x, y, z with respect to volume. See, we're no longer looking at adding up over little areas. We're taking that box and we're cutting